So we have the final part of the course on DG methods, and then today we can stay here indefinitely in principle. But then we will have 2 breaks after 1 hour each break. So.
Okay, so today I will talk about the second part of DG methods. This will be for PDEs with higher than first order derivatives. So here's an outline. So I will give an introduction, and then we will talk about, is that wavy or my eyes? A bit wavy from, if you read it from this.
I think it's sharp, yes, but it is wavy.
Wavy, yeah. Anyway, wavy is good, wave equations. So we'll talk about the DG methods. For convection diffusion equations, this will be equations with the second derivatives. Then other DG methods for diffusion equations other than LDG. And then higher orders, for example, KdV equations will be, which will be PDEs with third order derivatives, and LDG methods for even higher order, either diffusive or dispersive wave equations. Okay, and then the second part, we will move on to talk about extension of positivity preserving to these higher order derivatives, multi-scale DG, and energy conserving LDG, if we have time to talk about all three. Otherwise, we will give 1 or 2 examples. Okay, so an introduction here. So last time, on Friday, we talked about DG methods for hyperbolic equations. They have been very successful, have been developed for many years, from linear to nonlinear, which essential ingredient there was to borrow the concept of upwinding numerical fluxes, right, based on upwinding from methodology of finite volume schemes. Okay, so let us try to see how to generalize this to diffusion equations, second order Navier-Stokes equations. For example, let's look at the simplest prototype equation, which is, of course, the well-known heat equation, ut minus uxx equals 0 with simple initial condition. Now, we know how to deal with conservation laws, so it's ut plus fux equals 0. And we would like to know how to treat heat equation. So the first very natural thought coming to our mind would be that, well, you can see that heat equation is also a conservation law. If you replace Fu by minus Ux, right? So then it becomes Ut plus parenthesis minus Ux parenthesis sub x, which is Ut minus Uxx equals 0. So formally, if you replace f of u by minus of ux everywhere in the old DG scheme for conservation laws, you would get 2, which looks like a scheme for solving the heat equation. So here used to be minus fu times vx dx. Now it becomes plus u sub x vx dx. Here it used to be plus f of hat, which is the numerical flux at j plus half. Now it becomes minus ux hat of j plus half. So formally, you would immediately get so-called a DG scheme for solving the heat equation by replacing Fu by minus Ux everywhere. Of course, this does not completely solve the problem, because here the numerical flux used to be based on monotonicity for scalar case and based on either exact or approximate Riemann solvers for systems. So these were both based on hyperbolic equations, right? Upwinding principle, hyperbolicity, and so on. So if here you have this Ux hat, certainly you cannot use the same principle, because for heat equations there is no upwinding and so on. Okay, but you say, well, this is not a big deal, because we know that for heat equations, information is propagating in all directions equally. So there's no preferred upwinding direction, so we shouldn't prefer one direction over the other. So if we have information of Ux from both left and right, the most natural way of trying would be to just take the arithmetic mean. So you take the average of ux from the left and ux from right. Remember, u is a polynomial on both sides. Certainly ux is also a polynomial of 1 degree lower on both sides. You certainly have a value of ux on the left and ux on the right. Just take the average of them for first try, right? So this, if you put this in here, then you immediately get a scheme 2, which is a scheme, DG scheme for a Healy equation, which looks very similar to the DG scheme for hyperbolic conservation laws. If you discretize this time t, again by Runge-Kutta, so first forget about the efficiency, so do use Runge-Kutta, and delta t is proportional to delta x squared. Then you can get a scheme which you can compute the solutions for Healy equation. Looks like the scheme is very easy. You can change your hyperbolic code maybe in half an hour to get this code, right? All you need to do is that whenever you see minus fu, you replace it by ux, which is again a polynomial of 1 degree lower, and this flux, you replace it by this average arithmetic mean. However, if you go to the computer and do numerical experiments for this scheme, you will get horrible results. So first of all, you try to do as numerical analysts do, you perform a series of computations based on different mesh sizes, do a grid refinement study. Delta x is here. And you can see that the error basically stays constant. So there's no convergence. The order of convergence is 0, which means the constant error when you refine the mesh. And if you plot the picture, this is what you get. Well, I'm sorry that there is actually a line, a solid line, which disappeared on this screen. There is a solid line, which is somewhere between these two, which is the exact solution. And the symbols are the computed solution. So you can see, well, you cannot see, but you can imagine there is a solid line here, solid line up to this point, which is the exact solution. The exact solution and the computed solution, they look, the shape look the same, but the height looks different. And also for k equals 1, which is piecewise linear, and for k equals 2, which is quadratic, they perform differently also. One of them is taller than the exact solution, the other is lower than the exact solution. But anyway, this picture and also the previous table convince us that the scheme has something wrong with the scheme. So, and the worst part of this is that when you perform a grid refinement study, here I'm plotting only one grid, right? But you can perform a grid refinement study until maybe 6,400 points, 6,400 points, and even more. You will see that the solution stays with the symbols. So that means it looks like the scheme converged to something, but that something is not the exact solution. It looks in this also. So then you ask yourself a lot of questions, right? So what went wrong, and whether it is indeed an inconsistent scheme or what else. So this actually puzzled us for many years. We know that something's wrong, but we don't know what. Unfortunately, the finite element methodology, the theoretical framework, helped us in the hyperbolic case very nicely to prove stability, accuracy, and convergence and everything. But if your scheme happens this way, then the finite element methodology is not very easy to use. Because the finite element methodology is such that if you have a nice scheme, you can show that it is nice. If it is not a nice scheme, then all you can show is that you cannot show anything, but it's very hard to pinpoint at which location the scheme went wrong. So this took us some time. So what we did was that we rewrite this scheme by choosing degree of freedom, by writing it as a nodal-based DG. So choosing degree of freedom in a finite difference way, so that we can rewrite this scheme as a finite difference scheme. Once you write it as a finite difference scheme, you can perform a finite difference analysis. This we also know, right? So you can perform truncation error analysis to see if the scheme is consistent. You can perform a stability analysis, L2 stability analysis based on for normal analysis and more further to to see if the scheme is stable. Now this one is also tough in this case. So basically we write down this scheme in a finite difference way. We also wrote down the scheme, which is the good one, which I will describe later, the LDG scheme, also as finite difference. We perform analysis. So this is what's done with my collaborator. This Zhang is my collaborator Mengping Zhang in China. So basically we looked at both schemes. First of all, we look at the truncation error. And after a couple of hours or days, so Mengping came back to me to say that, look, this bad scheme is actually consistent, right? So truncation error is the first order, so it's consistent. And that good scheme that I will mention later, the LDG scheme, is not consistent. So bad scheme. Are you sure? Maybe you got things backwards? No, not backwards. So double checked. This is the case. So this scheme is actually consistent. So I will explain what happened to the other scheme, which is inconsistent but a good one. But here, if it is consistent, then we know that there is a Lux equivalence theorem saying that if you have a linear scheme, finite difference scheme, if it is both consistent and stable, then it is convergent, right? It's a theorem. So since we have seen from our own eyes that the scheme is not convergent, and if it is also consistent, the only possibility is that the scheme is actually unstable. But this is very strange, because usually when you have an unstable scheme, you can perform numerical experiments, you can immediately see the instability. If you go to the computer, use a very refined mesh, run it for many, many time steps, it will blow up on you, right? This is our experience. But here, I mentioned that the scheme, you can go to the computer using few thousand or tens of thousands points, run many, many time steps, and it's still nice. You still don't see any inconsistency. So what was happening is that this is actually, so with a very subtle analysis here, we can see that it is unstable, but it's not the usual instability that is an exponential growth type instability. If you perform a von Neumann analysis, in other words, if you run Fourier symbols and look at the amplification factor, look at the eigenvalues of this amplification matrix, eigenvalues are all fine. They are less than or equal to 1. It passes the von Neumann analysis very easily. And sometimes you will say, okay, then maybe the amplification matrix is not diagonalizable. That could also happen, leads to instability. And it is actually diagonalizable. So every traditional check would not give you conclusive remarks. So finally, what you really have to do is to compute this amplification matrix G raised to power n explicitly and look at this final matrix, G to the power n. And this G to the power n, the L2 norm of this G to the power n is unbounded, but only very weakly. Is proportional to n, to the number of time steps. So in other words, it is unstable because you know that stability means that when n goes to infinity, delta t goes to 0, n times delta t is bounded by capital T, then the G to the power n should be bounded. This time, G to the power n is proportional to n. So it's unbounded, that's the definition of instability. However, this instability is very weak. It is, if you think about it, if you do one iteration, the amplification is only by proportional to the number of time steps. So if you run it for 10,000 time steps, it is raised only to the power of 10 to the 4, right? So if initially the perturbation is at the round-off level, which is 10 to the minus 15, double precision, if you run it 10,000 time steps, the amplification is only up to 10 to the minus 11. You cannot see 10 to the minus 11 by your eyes. If you want to see it by your eyes, you really have to run it 10 to the positive 15 time steps, which is not possible.
Use single precision.
Use single precision. So this is really a very subtle instability. However, mathematically, this is the reason that the method performs as it performs. So it's a very good textbook example to show the power of numerical analysis, that you really have to check both consistency and stability before you are assured that the method is useful. So because of this, this is a good example to show that DG methods, when you try to generalize DG method to beyond the hyperbolic, you have to be super careful because there might be such pitfalls that you might get completely wrong things. So you would have to either do numerical tests or better still perform some analysis, at least for simple equations, and make sure that your method is a good one. Okay, so this is a very a good story on DG. So then, actually, let me also mention that this method, which is unstable, but numerically you actually can compute. What you see is an amplification, which you see the solution, which is not the exact solution, but the shape is like the exact solution, and the height is different. This method is actually used by engineers and published papers in a AA journal. Because if you think about it, if you go directly to compute the Navier-Stokes without going through the heat equation step, you know that for Navier-Stokes equations, you typically do not have exact solutions available to you. So you compute, you plot color pictures, beautiful, stable, and pictures are beautiful, then you say, well, it's fine. Maybe your advisor will tell you to, okay, look, you have to refine your mesh and you should get the same result. Well, you do, right? For this particular case, you can refine your mesh, you still get the same result. So, oh, this is reliable, so we can publish it. So this is, again, you have to be really careful before you do that. So I would advise that for every new method that you really have no feeling, you don't jump directly into the application equation, which is three-dimensional Navier-Stokes. You probably try to start with simple ut plus ux equals 0, ut equals to uxx. Just make sure you understand the method, right, thoroughly, and before you go to the more complicated ones. But this is not absolute. So it's also true that sometimes people who do not have barriers, internal barriers, who would want to try things will get good results. So immediately, right? So this is another good example of engineers doing things which would be very good. So for example, this good method, which is called LDG, local DG, I will explain where this local is coming from. It came from the work of Bassi and Rebay in JCP 97. Bassi and Rebay are both engineers in Italy. So basically the story is that they basically wanted to find some methods to compute compressible Navier-Stokes. And they were, since they were in Italy, they were chatting with a mathematician whom they know, who is Affio Quattroni in their university. Quattroni by that time was actually in Minnesota as a professor. Actually, the University of Minnesota was trying to recruit him by that time. So Quattroni was actually on the faculty of University of Minnesota for a couple of years. So he knew about the work of Cockburn and Shu on DG methods. And when Bassi and Rebay asked him what method should they try, they say, well, it seems that there is a method of something by this Cockburn and Shu. Maybe you can take a look. So they took a look. And they found out that Cockburn and Shu, the method was only for Euler equations. But they didn't think twice. They didn't ask us either. They correctly think that, well, if you know how to solve Euler, you know how to solve Navier-Stokes. So they went ahead to solve Navier-Stokes this way. They rewrite the heat equation into a first-order system by introducing an actual variable q. Q equals to ux, and ut equals to qx. So then it becomes a first-order PDE. First-order PDE, then, at least formally, you can write down the DG scheme just using what we talked about on Friday, hyperbolic equations. This first one is exactly like what we talked about on Friday. This is ut minus q sub x equals 0, so q is that fu. So it becomes this. And the second equation, of course, here, you don't have q sub t, so that's the only difference between a hyperbolic equation and the informality and here. But this part is identical, right? Because this part is u sub x, which is again look hyperbolic. So you can write down the DG scheme at least formally this way. And of course, when you write down it this way, you still face the issue of how do you choose numerical fluxes, the guys with the hat. Again, there's no upwinding. However, you can use the same argument to say, okay, look, it is a parabolic equation, information propagates in all directions equally. So why don't we just take Q hat to be Q minus plus Q plus divided by 2, and U hat equals to U plus plus U minus divided by 2. So everything is treated in a symmetric way, and that works. So they have this thing, this method, and they actually get good results. Let me mention what is the word local. Why is it called local DG? If you look at the second equation, suppose we are using an explicit time stepping to discretize this scheme, then at time level n, we have a numerical solution which is U, which is a polynomial, piecewise polynomial, right? Each cell it is a polynomial for the solution U. And then from this second equation, because this part involves only U, so you can immediately, this guy is just a local, it's integration over ij. So this guy involves only the local mass matrix. I mentioned on Friday that this local mass matrix, first of all, is very small. In 1D, for example, piecewise quadratic is only a 3 by 3 matrix. You can invert by hand. And also, if you take a locally orthogonal basis, this is even a diagonal matrix. It's nothing to invert. So you can see that from the second equation, you can immediately write down Q, which is a local polynomial, by using information of U only in yourself and in your two immediate neighbors through the numerical flux, right? So you have the polynomial U of the 3 cells, you immediately get the polynomial Q in your current cell by either inverting a small mass matrix or inverting nothing if you have a diagonal orthogonal basis. So this is why this variable Q is not a real variable. You can say that it is just a rewriting, some combination of U, right? Because you have this U of yourself and the two neighbors, and then you massage them, it's a matrix multiplication of the coefficients, you immediately get Q. So Q is a placeholder, you can say. It's not a real independent variable, because you get it directly from U and locally, right? No global matrix to solve. So this is why the method is called local DG, because Q, the auxiliary variable Q, is obtained locally from the true variable U. So you never store this Q, right? You store only U. When you need Q, you solve it locally, use it, throw it away, basically. So that's why local DG is essentially also only with the variable U as your main solution. This is to be compared with the so-called mixed finite elements, which also writes this PDE into two systems. For mixed finite elements, this variable Q is a global polynomial. It has to be solved from U by solving a large global linear system. So that's a real variable because you cannot really immediately get Q if you have U. So that's very different. Okay, so you use the well, here we wrote here a different thing, but if you use just the central difference, U hat and Q hat, if you use U minus plus U plus over 2 and Q plus plus Q minus over 2, you will get good results and you get very nice both tables of convergence and good pictures. So you see here is again, right, the engineers, they get good results without, just by common sense, without asking us. So I would say in this case they did the good thing, because if they wrote an email to us asking, yeah, you saw your paper only dealt with Euler equations, so what should we do with Navier-Stokes? We would have told them that, well, we don't know how to do Navier-Stokes. Probably you would like to use something else for the viscous part. By that time, actually, we had papers ourselves that we treated the viscous part by mixed finite elements. So that's a terrible method because it's hybriding DG with traditional finite elements and it's quite messy. Because we did not think that this kind of simple approach would work, right? So this is, we of course, with mixed finite elements, there are a lot of restrictions on what polynomial space you can use for Q. You have a polynomial space for U, you have a polynomial space for Q. For Q, you basically have to, these two spaces would basically have to match. So they have names attached to them. Ravia-Thomas space pair, for example. You have, for U, for Q, two different polynomials and so on. And then you get stable methods. But here, it looks like even if you use the same space, right? You use piecewise polynomial of degree k for U, piecewise polynomial of degree k for Q, you already get good results. It's too good to be true, right? But since the engineers already did the computation, we thought that, Cockburn and myself, we thought that we need to look at it mathematically a bit more. So we did, and we found out that yes, indeed, the method is actually stable and convergent with optimal error estimate. With a slight change, so you can actually use this Q minus plus Q plus divided by 2 and U minus plus U plus divided by 2, this is central fluxes, that's fine. But they are not optimal in the sense that they produce L2 errors which are one order lower for certain polynomial of degree k. So I don't remember it's even or odd. One of those cases you will lose one order. This is not optimal. However, if you choose them this way, this is called alternating. So if you choose U hat to be U minus, Q hat to be Q plus, or vice versa, then you will get an LDG method which is accurate, which is stable and accurate to any polynomial degree. So optimal accurate to get h to the k plus 1 with polynomial k. Okay, so this, you see, this is good. This is an example to show that sometimes mathematicians are confined by their own barriers, right? So we did not do this because we did not think that it was possible that it would be you would have no restrictions on the types of polynomial space for U and for Q. But it actually turns out to be the case. So the method becomes quite simple, right? So you can see the method is here. You have this for U and this for Q. So basically, if you have explicit in time, the coding is also very simple. This part is very similar to a hyperbolic subroutine, right? Because remember, this U hat, now I choose one-sided, right, alternating. So U hat is U minus, which looks very much like the upwinding flux you used before. So the same subroutine could be used to compute this part from your hyperbolic code, and then you get Q. Once you get Q, you put Q to the subroutine and change this flux to Q hat equals to Q plus. So that means you change the hyperbolic code just by changing the wind direction. Then you get this part, and then you can update U. So basically, to rewrite the code from the hyperbolic code to this LDG code, you would take maybe 1 hour, maybe even less, because you basically copy the old code and use it twice, right? And then that's it. So this LDG method turns out to be very easy in implementation as well. You don't have to store this Q globally if you don't want to, because as I explained, this is a local placeholder. Okay, and this method works so nicely, you can prove it is L2 stable and optimal convergent, h to the k plus 1. And the good news is that this is also true for general systems. But first look at the heat equation, the same table as we have seen before, but now with the correct LDG, then you immediately see that you have second order here, you have third order here. Now, let me come back to my remark before I mentioned that when we were looking at the bad scheme, we also wrote this scheme down, because both of these two schemes, if you write them using nodal basis, then they become finite difference schemes. The only difference would be the coefficients. So they look very similar, so it's a finite difference scheme. for the bad guy and find a different scheme for this good LDG. I mentioned to you that we did this local truncation error analysis. The bad guy actually is consistent. The local truncation error is first order, goes to 0. This good guy has a local truncation error which does not go to 0. So it looks like this good guy, by truncation error analysis, is inconsistent. By that time, that also puzzled me, because by that time, I did not know what this is, right? Until I looked at literature, I found out that this is actually not very common, but it's not unseen either. This is an issue which is called, so there's no blackboard here, but anyway, it's called supra-convergence. You have heard super-convergence, right? Super-convergence means that you have a method which you expect it, for example, your method using polynomial of degree k. You expect the convergence to be k plus 1. However, for some reason, maybe in negative norm and so on, you actually see convergence of degree higher than k plus 1, let's say 2k plus 1. This is usually called superconvergence. Now, what is supraconvergence? Supraconvergence means that you have a method which is polynomial of degree k. You expect that you can get convergence to k plus 1. Numerically, you also see convergence to k plus 1, like here. However, when you perform the truncation error analysis, you get a truncation error which is lower than the order of k plus 1, or even inconsistent. That could happen. So the local truncation error may be predicting errors larger than the actual error, right? Or even predicting inconsistency where the actual scheme is perfect. This, of course, you prove that it is perfect by using not finite difference methodology, but finite element methodology you can prove. But what went wrong with this finite difference is this supra-convergence, that local truncation error can be misleading in some situations, and you have to perform local truncation error when you rewrite the scheme in another way. Because the schemes usually can be written in several different ways, mathematically equivalent, but they look different in format. And then one of them, maybe you can get the correct prediction, but others, you predict errors bigger than what they should be. And this is called supraconvergence. This was actually studied in detail in some papers in late 70s and early 80s, very long time ago, by the school of Kress, Hans Kress of Sweden, and UCLA. So what he did, he has also his student, for example, Manteuffel. What they did was to look at ODEs. For example, you have a high order ODE written as a low order system, very similar to this. For example, if you have y double prime plus something like a times y prime plus b times y equals to f, you call y prime to be a new variable z, and then you write a system for y and z, and then you write down your scheme this way, or you directly discretize the y equation. So these two schemes, even though mathematically they are equivalent, while you perform truncation error analysis, they will predict different things. So then they study supraconvergence from this point of view. But anyway, this is just a caution. So next time when you see schemes that you perform truncation error analysis, they don't predict what you numerically observe, don't be surprised, right? This could happen. It's okay. It's okay. Trust the numerics. Yeah. Or change your proof. So proof in another way. So this is also very nice. So the good news is that what I said before can actually be generalized to this very, very general convection diffusion, nonlinear convection diffusion equation. So this is multidimensional. As long as this Aij of U form a semi-positive definite matrix, it will be fine. So this is the most general form of possibly degenerate convection diffusion equation. So you can degenerate, so it does not matter. The method will still be stable, and you still can perform error estimates. So the LDG method is actually quite general from this point of view. This is also one thing which is good about finite elements for DG, for example. If you have a finite difference scheme, you worked out a finite difference scheme for Healy equation, you write it down, you proved consistency, you proved stability, you proved convergence. Then you try to generalize your finite difference scheme to this in multi-dimensions on triangles and so on. It will be a major task. It's really a big jump, right? You need to do a lot of new work. However, for DG, once you have done it for Healy equation, I would not say you don't need to do any work, but to jump from the Healy equation to this is not that a big jump. So I did not write the full thing here, but I could, for example, in lecture, I could do it in 1 hour or so. So it's not a lot of difference. The principle would be the same, still integration by parts, still with choice of numerical fluxes is still alternating. So every essential ingredient would still be the same. And you prove stability, you prove error estimates, and everything. The result carries over to very general situations. Okay, so you can get some, in this lecture notes that I mentioned the last time. You get some feeling. Let me show you how this is done. I don't want to do that multidimensional thing. It's too notationally heavy. So I'll show you the example so you can be convinced it's similar to before by this one-dimensional example. So it's a one-dimensional nonlinear convection diffusion. So AU is positive. So you introduce a new variable. Remember, the new variable is related to UX. So what new variable should you do? Well, it turns out that this is the best way of introducing the new variable. Remember, this AU is positive, bigger than or equal to 0. Because it is positive, I can take the square root, right? I take the square root, I call it BU, which is again a new function. And then I call this capital BU to be the primitive function of small bu. And this Q, this new auxiliary variable Q, is introduced to represent the capital BU sub x, which is small bu times Q parenthesis sub x, right? Because it's capital Bu sub x is B prime of UU sub x. B prime of U is B prime of U is B small bu. Yeah, so small bu U sub x. So there's another Bu here. So it's a small b square of u, which is small a of u times u sub x. So this is the way to introduce the auxiliary variable. Then this equation is written as a conservation law, right? Here you don't see any second derivative anymore, so it's fu is bu times q. It's the first derivative. Here only also first derivative. Then you rewrite it into a scheme. So you see this scheme now is the first scheme. The first equation is integrated by parts. You have this flux, and you have this numerical flux, or those hats. And the second equation, which is Q equals capital Bu sub x, is B, capital B hat here. So this is just to rewrite the previous sort of a hyperbolic equation of first order PDE into a DG scheme. Now the numerical fluxes, let's look at the numerical fluxes. It's alternating. You see, Q equals to Q plus and B equals to BU minus. Right? So you see this B hat here and Q hat here. Q is Q plus and B is B minus. Alternating. You can do it the other way. You can put minus here, plus here. This is small b hat, which is here. Remember, what is small b? Small b is the derivative of capital B. So small b hat is chosen by mean value theorem. So it's basically the derivative of capital B, right? So by mean value theorem, this is capital B prime at some c, which is a small b. So small b hat is very easy. It's just a divided difference, but these two are alternating. So once you do this, I mentioned also that the alternating can be the other way. You could also put, remember that was a plus here, you can put a minus here, but then you put the plus here. This doesn't change. So you can see that you can still solve coding-wise, you can still solve this thing from the last equation. Once, for example, I'm marching from time level n to time level n plus 1. So at time level n, I already have a polynomial for u. So I use this polynomial for u, which is here. Let's see. Yeah. Where is? I think I made a mistake. Apologize for that, right? Did I? No, I did not. Okay. So here, this is u. So I already have polynomial at time level n, degree k polynomial, which is called UH. I put UH here in this nonlinear B, and this looks like my conservation law code, right? This capital B of US looks like f of ux, f of u. Then it's a B of u, and then you put it in here, compute this part, and then you can get Q, polynomial Q. You use the polynomial u in your own cell plus 2 neighbors, actually only 1 neighbor because the flux is one-sided. The flux is one-sided, 1 neighbor. And then you get Q here. Once you have Q, you put it in here. This is the Q hat, and this needs u. And once you have this, you can then update the solution u. Again, the nonlinear code, the code for the nonlinear convection diffusion equation is a direct change from the code for nonlinear hyperbolic conservation law. Few lines change. So you can get that. Okay, so that's very nice. So this is how you prove in Wang Shu. You prove this cell entropy inequality, which means ddt of u plus q square plus a flux difference is less than or equal to 0. This is a very strong statement, because if you sum it up, then these telescopes, so you get that the stability in L2 norm for both u and q, for both u square and q square. So it's a very strong stability result, similar to what is obeyed by the solution of the PDE. So this is, yeah, so you get this stability estimate, right? ddt of the L2 norm square plus this positive thing which involves the derivative. Remember, q approximates the derivative of u. So this sum of these two things is less than or equal to 0, which is the bottom, yeah. The L2 norm of the solution at the later time t plus the L2 norm of the derivative in space and time is less than the L2 norm of the initial condition. Notice that the exact solution of the convection, nonlinear convection diffusion equation also has this property. So we obey the same stability property as the exact solution of the PDE. You can also prove error estimates. Yeah, so this is very nice. Let's see, how are we doing? Yeah, we are doing fine. Okay. So let us mention several other DG methods for diffusion equations before we break. The first DG method, well, this is the LDG, right, which is a popular method, but there are also several other DG methods for solving diffusion equations. For example, the internal penalty DG methods it is done this way. So you have this heat equation. I again use the heat equation as an example. You multiply it by a test function v. You integrate it by parts. You get this thing. So far so good, right? It's a little bit like the bad DG scheme that I shown before. But then a good way of explaining the internal DG is to first sum it up over cells. So I summed up this thing over j, this I sub j summed over this small j. When you sum up, these two things will telescope. But of course, there's a plus here, there's a minus there, so you get the jump of the test function v when you telescope. So you get this, 16, when you sum it up. So it is a sum of these terms, ux times vx, integration over the cell, plus a term which involves the interface terms is ux at j plus half times the jump of v. Okay. Now, if you want to convert this to a scheme, what you do is that you want to say, I want to find UH in this finite element space such that for any VH in the finite element space, I have this. So every term is repeated, except here, this ux at j plus half does not make sense, right? Remember, if you replace the exact solution u, which is smooth, so certainly you can say ux at j plus half. But the numerical solution is a piecewise polynomial. At j plus half, you have the left and right. You don't have a single value ux. So you cannot use ux here. But one thing you could do is you take the average, right? You take the average. You can take the ux on the left and the ux on the right. You keep this thing the same. So this would be a scheme. This is exactly the bad scheme I have shown before, the one which produces this wrong result. This is what you get when you go from the weak formulation directly to DG, right? So certainly this scheme is not usable. So how do you modify this scheme to make it usable? So first you look at what could be wrong here. One thing what you immediately notice it could be wrong is that this is not a symmetric scheme. Remember, the heat equation, the heat operator is a symmetric operator, which means if you replace u by the test function v, you get the same thing. Here, you replace u by v, you get the same thing here, you get the same thing here, but you don't get the same thing here. So these interface terms are not symmetric. So this is your first natural observation. So how do you fix that? Well, you just add another term to make it symmetric. So you add this term, which was not there before. So you just replace this u by v, replace this v by u. Same term, you just repeat and add it here. You might say, can I add it? Does it introduce some inconsistency? No, it doesn't, because for the exact solution u, it doesn't jump. So what you have added here, if you replace uh by u, it is 0. In other words, you have added something which is purely numerical. If you replace your numerical solution by the exact solution, then this additional term drops. So you are not adding an inconsistent term, you're adding some term which is allowed. Okay, so you can put this in, then this whole business becomes symmetric. Unfortunately, even now, the scheme is symmetric all right, but it is still unstable. So, bad luck, right? Bad luck. Still unstable, so what do you do? Well, add more, right? So this is how people do things. It's unstable. Add one more term. Okay, add this term. So I add one more term which is huge, humongous. It's alpha over h. And jump of u times jump of v. Why is this a good term? Because if you replace v by u, this is a square with a negative sign with a huge coefficient, so that stabilizes. This is on the right. If you have a negative term on the right, it certainly stabilizes your scheme, right? So you can imagine that by tuning this alpha sufficiently large, I could get a stable scheme. Indeed, that is the case. There's a mathematical theorem saying that if alpha is large enough, the scheme is stable. 1982, very early. Right? Oh, 78. Yeah. So people realized that you need to add a lot of things to it before you can stabilize. But of course, yeah, too many things. You can argue if this is a good scheme or not. It is stable. It's optimal convergent. The bad part is that there's a parameter you have to tune, this alpha. If it is too small, the scheme is unstable. But the proof does not tell you how large alpha should be. So in practice, you have to test and see what alpha you put. You don't want to put too big alpha because this is an artificial term. So if you put alpha too big, it affects your performance. Maybe it's stable, but it may not be that accurate. Okay, it affects, of course, the coefficient here in the error estimate. So this is one possible internal penalty scheme. It is called SIPG in the literature, or symmetric penalty method. So whenever you see symmetric penalty method, it is this method. We have this alpha here that you can tune. So is there anything else? Well, there's another method which looks funny. What happens if I change the, remember this term, both of these terms were added on later. They were not there in the beginning. So suppose I don't add this term, of course it's unstable. But suppose I change the sign here to plus. But you might say, well, what's the point? I put a negative sign here for a purpose. That was to make the whole business symmetric. If you put a positive sign there, what is your purpose, right? Well, it could be that the student made a mistake in coding. In adding a term, right? So he's a student, so he adds a term, he made a mistake in coding. So if you make a mistake in coding, you get this scheme. It's not symmetric. So this is called non-symmetric internal penalty method, NIPG. NIPG. So this method, well, the joke, I do not know if it is the truth, right? The joke was that this Baumann was a student by that time and he made a mistake in coding. Maybe not. Anyway, if you change the sign here, hey, then the method becomes stable. Yeah? You don't need an extra term afterwards. It's a stable method, but of course it's still not symmetric. But it's okay, right? It's a stable method. So this method is actually already usable. It's stable. It is convergent, but it's not optimally convergent. So for some of the case, I think it's either even k or odd k. It goes the other way with the LDG with central flux. One of them lose one order in one set of case, the other lose order in the other set of case. One of them in even, the other in odd. So in half of the time, this scheme will lose one order on you. So you for example, polynomial of degree k, you should get k plus 1's order accuracy, but you only get k's order accuracy. So, but at least you get something. It's convergent, it's stable. So this method also has been used, and it's referred to as NIPG. So it's non-symmetric internal penalty method. Okay, so these are the internal class of internal penalty methods: symmetric, non-symmetric. You can see that there are people like Babushka and so on involved in the analysis of these type of methods. Okay, there are other types of DG methods involving internal penalty methodology. For example, the direct DG method of Liu and Yan, and other methods. Ultra weak, I think I should take a break, right? Okay. So the last item in this convection diffusion DG is the ultra weak discontinuous Galerkin method. This was in a paper by Chen and myself, Inda Chen and myself in MassComp 2008. So what this method does is that it does integration by part twice. So remember, it used to be that here you stop at u sub x times v sub x, and you have two boundary terms. Now if you do one more integration by parts to throw all the derivatives to test functions, then you have, instead of two boundary terms, you have four boundary terms. This certainly is an equality satisfied by the exact solution. Ultra weak comes from the fact that you throw all derivatives to test functions. Weak means you throw about half your derivatives to the test function. You still keep equal load, right? You still keep half of the derivative, then you throw half of the derivative to the test function by integration by parts. This is weak. Strong means that you keep all your derivatives. So the test function is just a test function, no derivative. Ultra weak means you throw all derivatives to test functions. So then, if you try to write down the DG scheme for ultra weak, then what you get is that you find UH such that this equality holds for every test function V. Here now I have two numerical fluxes. I have UX hat and I have U hat, because I have done integration by parts twice. So I have four boundary terms, two numerical fluxes. And if you choose the numerical fluxes this way, unfortunately, for all even order, including second order PDEs, diffusive PDEs, ultra weak formulation also require this term. So if you just do plus minus, it's unstable. So you need to add this term, which again looks very much like the symmetric internal penalty method. You have the alpha over H here. When alpha is non-zero, this thing is stable. Okay, so you have alpha positive, for example, sufficiently large. This thing is is stable. Okay, this alternating thing is the same as before. You can put a minus here, plus here, or plus here, minus here. Doesn't matter. But this term must be there. Later we will see that actually in the same paper, this ultra-weak formulation is done for PDEs of all order, every order. So, but from second order, second, 4, 6, 8, all of them, you need this term. But 3, 5, 7, and so on, all of odd order PDEs, you don't need any penalty, so they will be automatically stable. Okay, so this is a method you could use also. Now, there's actually you were talking about this argument of LDG versus all these kind of methods, internal penalty, symmetric, unsymmetric, ultra-weak. The difference is that in these kind of methods, you are dealing with a single polynomial u. You do not have auxiliary variables p for ux and so on. So it's psychologically simpler, I would say. So even though they have these parameters and so on, all the anti-symmetric thing, they don't have parameters, but they lose order of accuracy. There are still people preferring to use them because of simplicity. Yeah. So, and on the other hand, the LDG is much more sound theoretically because it's stable with no parameter to tune. It is optimal convergent. However, there's a psychological barrier that you need to do a lot of things for these auxiliary variables, coding-wise, and so on. So yeah, so it's a debate, yeah, which one should use. But I have outlined all these options, so in your applications, you might want to try 1 or 2 of them, and then finally settle down on one that would be, to your taste, is the best balance.
Can't you take alpha as just a heat conduction coefficient?
Well, this, again, the proof, you can see the proof. The proof still needs alpha to be sufficiently large. So
it cannot be just taken as...
Cannot just fix it at 1, for example. Well, in practice, it turns out that this alpha, well, in our code, it was probably 1, and it works. But
because in pilot volume schemes, you often take it as heat conduction coefficient or viscosity coefficient, which is 1 in this case. Yeah, but you cannot prove that one will work. Yeah, you can only prove that when it is sufficiently large, it will work. Yeah. Okay. Okay, great. So basically now I finished the description for DG schemes for convection diffusion equations. I hope I have introduced most of the available options to you, of course, very briefly. So then you have a vague idea, and you know if you really want to use it, you can dig out the literature or lecture notes, try to code up some simple cases, compare yourself with yourself, and then choose one. Okay, now let me move on to even higher order PDEs. KdV, which is a third order PDE. You can see here there are 3 derivatives here. First derivative and 3 derivatives. In general, of course, you can put this kind of terms, very, very nonlinear. Or in multi-D, you can put this kind of terms. So this function R, G, R and G, here is a bunch of functions. These are arbitrary nonlinear functions. And these kind of things come from mostly from mathematical physics, that people have all kinds of strange functions when they model certain nonlinear waves. So you can open a book of, for example, Journal of Mathematical Physics. So in many issues, you get all kinds of very strange looking PDEs. That is a simplified version of some, actually simplified in terms of dimension and so on, but more complicated in format. Maybe the original equation is a very simple Euler equation or whatever, very simple, but when you simplify, it becomes more complex in terms of nonlinearity, but of course it's lower dimension and so on, fewer degrees of freedom. So we would like to see if for these kind of equations, we can find a DG scheme which maintains stability and accuracy. So we use this as an example to demonstrate the idea that the scheme will work for these general cases.
Actually, we use this as an example. We always do the simplest thing. So this was actually a PhD thesis, was done in a PhD thesis of one of my former students, Jue Yan, who was maybe more than 10 years ago at Brown. So she has just been tenured at Iowa State University. So when she was a student, I said, well, we know how to do ut equals to uxx. So should we look at how we do ut equals to u sub 3x, right? KdV. So of course, you can now guess what you should do, right? So if your LDG is to introduce an auxiliary variable to bring it to first order system, now you introduce two auxiliary variables, right, to bring it to system. So you introduce a variable q, which is ux, and you introduce another variable p, which is uxx, which is qx. And then this equation becomes a system of three equations, but each equation has only first derivative. Then you can certainly formally write down the scheme satisfied by these three equations. You can see you multiply by a test function v, test function w, test function z. I was joking that the most difficulty of doing this research is to find enough letters. So yeah, three already you run out of letters very quickly. So the v, and then you just multiply and do the usual dg, right? It's the usual dg. So you treat the first derivative the same way as you treated the first derivative when you were doing hyperbolic equations. First, let me explain. Well, all these heads are numerical phrases that I have to explain how to choose. However, let's look at the word LDG, right? Why it is still called local DG. Again, let's look at the explicit time matching, even though explicit time matching now is very inefficient, but let's psychologically first look at explicit time matching. So if you know the solution at time level n, so that means you know a polynomial for u at time level n, then you can immediately from the last equation compute q, right? Because this part depends only on u, which is basically your hyperbolic subroutine to compute the residual. So you compute the residual, you get this, you invert a small mass matrix, you get q, which is a polynomial. Once you have this polynomial q everywhere, or at least in yourself and your neighbors, you can then put this q into this subroutine, same subroutine. Well, not exactly the same, because q hat and u hat may not be exactly the same. We will explain what these numerical fluxes are chosen. But very similar numerical subroutine would be able to compute the residual here to get p, right? So you invert a mass matrix, a small mass matrix, you get polynomial p. Again, in yourself and your neighbors. Once you have this p, you put it yet again into the same subroutine. So it's very handy, right? You have this hyperbolic subroutine. For heat equations, you use it twice. Here, you use it 3 times. Copy and paste, 3 times. And then you get this residual, and that gives you the update for you. So coding-wise, this is trivial, right? If you don't care about costs. So this is Jue Yan, so he just used explicit time matching until he ran 2D. It looks impossible, then she tried something else. But yeah, 1D you could still use explicit time matching. So you get u at the next time step. So this scheme looks very similar to schemes before in terms of implementation. But however, how do you choose this numerical fluxes? Now, this, again, you need trial and error and some thinking. So let's summarize what has been done so far. For hyperbolic equations, we use the upwinding to guide our choice of numerical fluxes. For heat equation, which has no preferred wind direction, we used alternating. Alternating is actually central in a way, because if I eliminate the intermediate variable q and write down the scheme for u only, then for the lowest order case, k equals 0, if I use alternating flux, I recover exactly the 3-point central scheme for heat equation. uj plus 1 minus uj plus 2uj plus uj minus 1 divided by h squared. So from this point of view, the alternating flux choice is symmetric, is central, right? Because I use you once, I use myself once, I eliminate myself, so everything becomes symmetric. So these are two guiding principles. If I have waves which propagates in certain directions, I use upwinding. If I have just diffusion, the wave doesn't move but just get diffused, I use alternating. So how about this third order PDE? Is third order PDE diffusive PDE or wave PDE? Actually, the third order PDE is a wave PDE. This you can easily see by putting a single mode to the PDE. You just put the sign x as the initial condition, and you see what is the solution of ut plus u sub triple x equals 0. You get sine x maybe minus t, something like that. Sine parenthesis x minus t will be the solution. So it's a wave of plus t, okay? Well, this is the solution. So it's a wave, right? It's a wave, so that means it is very similar to first order PDE. You should probably use upwinding. So this is a good observation, right? I probably should use upwinding. Then it leaves you with two possibilities. The first possibility is completely upwinding, meaning that if the information is coming from the right, in this case x plus t, yeah, so the information is coming from the right, blowing from the right to left. The first possibility is that I have three numerical fluxes, p hat, q hat, u hat. I use all three of them from the right. So p hat is p plus, u hat is u plus, q hat is q plus. That's one possibility. Completely upwind. The other is I do upwind biased. In other words, I have three guys, right? So I don't have to be greedy putting all three on the right. I can put two of them on the right and one on the left, so it's still biasing to the right, right? So two possibilities. You try both. The three guy, if you put everything to the right, is unstable. This is not surprising. Don't be too extreme, right? You have to do things in a sort of balanced way. Even if information here is a bit better, you should not completely forget about your poor neighbor here. So still, you can bias to that, but don't use all three on this side. Anyway, if you put all three there, you can analyze the scheme is unstable. However, if you use two of them, there's the remaining question of which two. This, the intuition wouldn't be able to answer, I would say. Then you have to try to use theory to prove your guess is correct. So it turns out that the correct way to choose two on the right-hand side and one on the left-hand side is that this guy, this middle guy, which approximates ux. Remember, I have three variables. I have u, I have q, which is ux, I have p, which is uxx. This middle guy, which is ux, should always be chosen according to upwinding. Just turns out to be this way. So that's crucial. So the middle guy, the flux corresponding to the middle guy, has to be chosen in an upwinding way, which is here. It has to be chosen to be plus. And the other two, which is symmetric, u and uxx, you can do in an alternating way. So you can do plus minus or minus plus. Both of them will be okay. So this is the guiding principle. So for these odd order guys, you rank them in an order way, pick the middle guy, use upwinding. This is of course linear, upwinding is just the plus, but if it is truly nonlinear in that equation, you just borrow your monotone flux from your hyperbolic. You see the hyperbolic flux is also useful here. You just use the hyperbolic monotone flux or approximate Riemann-Solvers on this middle guy. So then all the remaining pairs you do alternating. So this works with, later you will see that the same strategy also works for fifth order PDEs, seventh order, 11th order, 9th order, whatever. So all the orders can all be done this way. Plus minus or minus plus. Then that's it. That's the scheme, right? Because you have seen the scheme is very simple. It's repeating your hyperbolic subroutine 3 times. The only thing is how do you choose the flux. Now I told you how to choose flux. The middle guy, you use upwinding. These pairs, you do alternating. So you write your code. Again, it's maybe a 1-hour job to convert your old code to this one because you copy your subroutine 3 times, change the flux a little bit. That's it. And you get, you see, very beautiful order of accuracy. K equals 0, you get first order. K equals 1, you get, where is the order? Here. Second order. K equals 2, you get third order. K equals 3, you get fourth order. Even starting with 10 points, right? You get quite a good order of accuracy. Yeah. Okay. So this is third order PDE. Now, for some time, actually for quite a long time, we can prove stability of this method. We can prove convergence, but we cannot prove optimal error estimate. So in the paper of Yang and myself, the student I mentioned who was doing this as her thesis, that was a paper in did I mention that paper here? No, okay, sorry. But that's a paper many years ago in some journal numerical analysis. We were able to prove only suboptimal k plus half order of accuracy because of a technical difficulty. And also we could not do so there are some issues there. But here, later we found out that actually these kind of wave equations, you need to use techniques totally different from diffusive equations. Essentially what happens is that for wave equations, the numerical solution, you cannot use the numerical solution to control the derivative. It's not like a heat equation, there's a diffusive effect. So the later time L2 norm of the solution and the L2 norm of the derivative is controlled by the initial condition of the solution alone. But you cannot hope for such things for the dispersive wave equation. The L2 norm of the solution can only be controlled by the L2 norm of the solution. The derivative of the L2 norm of the solution has to be controlled by the derivative of the initial condition, and so on. So there are a lot of complications. So this is a very recent paper, actually, in which we figured this out. And we were able then to show optimal error estimates for the schemes I described. So actually, these schemes are very nice. They are optimally convergent in L2. They are very simple to formulate. Their choice of numerical fluxes are very simple. No parameter to tune, and so on. So for these higher order PDEs, these penalty methods are being used much less. So because then you have a lot of parameters to tune, and it's very high order, it becomes quite messy. So for high orders, this kind of LDG thing seems to be a good choice. As I mentioned, the simple scheme that I outlined before can be generalized to this kind of multidimensional nonlinear PDEs with the same result as you have seen before, namely you have the stability. Yeah, so the stability is the most important thing. Cell entropy inequality and L2 stability. Yeah, here is the paper, sorry. The SAM numerical analysis 2002. You can see that it's 10 years to get this proof to optimal order of accuracy. Okay. Now I think I have listed several of these fancy equations from mathematical physics. And you can see the heavy Russian influence. All these names are Russian, I believe, right? Yeah. So this ZK equation, two-dimensional KdV equation, this one is actually less physical. It's not very physical. Even though it's mathematically pleasant, you can estimate. I mean, you can do directly the one-dimensional thing. The physical KdV equation is multi-D. For example, one of them is this ZK equation. This is ZK equation, and you can do the similar things. For example, you can get LDG methods for these equations, which are stable and with convergence proofs. So in these papers, we have done this. Let's see. Zeroth order diffusion limit zeros order dispersion limit of conservation loss. So you can see here it's like a KdV equation, but with an epsilon here, which goes to 0, which is very small. You see, it's very different from the diffusive limit, for which you have epsilon uxx here with a negative sign. So that one, basically, you get the entropy solution. This one, if epsilon goes to 0, you get a very funny, you get nothing. I'm sorry. Yeah, the resolution is not enough. So actually, there are supposed to be some oscillatory stuff there. But so believe me, I have seen a lot of things you do not see, so you have problems in your eyes. Oh, the display. You can see on the display.
During the break, we can.
Yeah, usually the correct strategy is that you keep your face straight and say, look at these pictures, right? They oscillate and so on. And then people say, oh yeah, gee, man. But if you laugh yourself, then yes. Something coming out. Some oscillation come out. But anyway, it's like in this limit, you get more and more oscillations rather than the pure shocked solution. So you get a very oscillatory results. So this LDG method, because it is stable, you can use it to compute such things in a very nice way. Okay, so let me move on to talk about the other diffusive equations. So this is a fourth order, so-called biharmonic type equation. Harmonic means second order, like a heat equation, right? Biharmonic means that you have fourth derivatives. So you can put the nonlinearity in as well. Here, AI is a nonlinear function. So this problem is a nonlinear fourth order PDE. You can do LDG, design LDG schemes for this one. It was done in this paper, and with error estimates given in this paper, Science Journal Numerical Analysis since 2009. Actually, these even order PDEs, they are very friendly to analysis. So the LDG scheme, even for very high order, even higher order, for fourth order, for example, in this paper we have shown optimal order L2 error estimates, not only for a rectangular mesh, but also for triangular mesh. So you can actually get optimal error estimates quite easily, unlike the previous third order one, which is really difficult. So this one, the proof is relatively simple because of elliptic regularity. Basically, once you have elliptic equations, this operator is very nice, gives you a lot of help in terms of proving error estimates. So I did not even write down the scheme. Okay, I'm sorry. Yeah, so the scheme is that you introduce, did I have the scheme? No, yeah, I'm sorry. I probably thought that I don't have enough time to go through this, but basically you can use mathematical induction, right? So this time you introduce 3 variables. So one of them for ux, the other for uxx, the other for uxxx. So they are altogether 4 variables. So altogether they are 4 numerical fluxes, right? For u, for ux, for uxx, for uxxx. So 4 numerical fluxes, they should be alternating. Yeah. So for example, u and uxxx forms a pair, which should alternate. Ux and uxx forms a pair, which should alternate. So you always take this way, symmetrically. And you don't have anything left in between because this is even. And the alternating thing can be changed independently. For example, minus plus, this is fine. Minus plus, plus minus, that's also fine, and so on. So all these combinations are fine. So each pair, you do alternating independently. Basically, that would give you the correct scheme. And you can show stability, and you can show order of accuracy. Like I mentioned here, the schemes analysis can be generalized to higher even order diffusive PDEs, and these error estimates can also be given for even higher order PDEs. So it's, but very few people use beyond 4. So biharmonic are still used. The 6 order PDEs, I have seen some usage, but higher guys, very few people would bother using them. Okay. So here you have the Kuramoto-Sviasinski. Sviasinski is Russian?
Sounds Russian.
Yeah. Kuramoto might be Japanese, right? Kuramoto, yeah, okay. Equation which looks like this. This is a fourth order PDE. This is just a coefficient. You can think of this coefficient as 1, for example. Then it is UX, X, 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 right? So it's a fourth order PDE. You can design the LDG scheme and then show that the scheme is energy stable, in cell entropy inequality L2 stability in this paper. For the simple one-dimensional version, not one-dimensional version, sorry, this is the type with all these nonlinearities. You can already show these things, but with the original Kuramoto-Sviasinski equation, which is nonlinear only here, and linear here, linear here, you actually get this kind of results. Chaotic. This is time, this is space. Looks like when you evolve in time, you get more and more structures. It is because if you look at the PDE, this term is anti-diffusive. This term is diffusive because this is the wrong heat, right? It's a plus UXS here. So it's a fighting between the anti-diffusion and the diffusion. However, of course, this thing dominates because it's a higher order derivative. So for higher order modes, this term dominates. But for lower order modes, they are more or less balanced. So that is why you can still generate a lot of structures in the evolution. But you will not get instability. All these structures eventually will be controlled by total energy. So it's a very nice physical model for studying many so-called chaotic phenomena. It's not really chaotic, it's deterministic, but looks like very many structures with pleasant to look, right? So n equals 300, you can see this solution. Okay. Another application is device simulation in semiconductor device simulations in all these models. These models are, for example, drift diffusion, hydrodynamic, energy transport, high field, kinetic, Boltzmann-Poisson models. You can design DG and LDG schemes and error estimates for these kind of things, and there are several papers devoted to the study of these models. Okay, and here, Carr-Hilliard equation. These are for phase transitions. So it is believed that these kind of equations will describe phase. Well, I'll show some numerical examples later. You see that it can evolve into clear phases between several different, clear boundaries between different phases. So it's again nonlinear diffusive equation. You can see that the leading term here is still, you see the two derivatives here, two more. So it is still biharmonic type. It is still a fourth order diffusive PDE, nonlinear though with all these B and psi prime. And there is a total energy associated with this system, and we can design LDG methods and prove energy stability for the LDG scheme. Again, all these things, it turns out that the choice of numerical fluxes are guided by this alternating principle. It's really amazing that it can go very far. So you basically, of course, you have to introduce your auxiliary variables correctly, but once you have done that, you mimic physics and you try to see how physics proves energy stability. You try to do the same thing. You choose numerical fluxes in an alternating fashion. You can see that actually numerically your solution also obeys the same inequality. So that is quite nice. So you get this in this paper, these papers. And these are the results. So at t equals 0, you have this randomized sort of input. And at a later time, you can see some structure evolving. And they evolve into larger structures, larger. Yeah. phase transition, right? So yeah, two-phase flows. I don't know how physical this is. Certainly there is still this psi and the function b there, which should be chosen in a physically relevant fashion. So for different materials or different types of phases. After all, these are mathematical models. But at least these kind of very high order nonlinear PDEs, if you want to solve them in a very reliable fashion, stable, energy stable, it still takes some time to write the general algorithm. The good news here, I want to emphasize again, probably for finite difference, there are a lot of, for spectral methods, there are a lot of computation of these type of things already. I would say that the DG method has a potential for unstructured mesh adaptivity, basically. So if you want to adaptively put more meshes around this interface and so on, then this method would have better potential than all the previous guys, because the finite difference is almost impossible. Spectral method also, if you don't do multi-domain, it's quite restricted in terms of how you can adaptive. But DG by itself is a completely adaptive method I explained, right? You can do H adaptivity, P adaptivity, and at the same time you have energy stability, which doesn't depend on how you choose H and P adaptivity. So that is probably the best hope in terms of adaptivity plus unstructured mesh. Okay, this is surface diffusion. I'm told that this is the diffusion on, for example, the sphere, the Earth, diffusion on Earth, on manifold, right? You have diffusion not on the plane, but diffusion on some manifold. But when you write it down, it looks like that. I think Q is related to, Q is area element, and H is mean curvature. Here, this capital H is mean curvature, which looks like that. So because of this Q, it becomes a complicated PDE, which is again high order, because the leading term here is again, I think, fourth order. Not 6, because there are some nonlinearities. Yeah, but yeah, because H here is 2, right? And 2 more, right? 2 more, right? Here 1. Here is another on H. You can forget about this Q, because this Q, for example, if this is constant, then Q is 1, right? This derivative doesn't count, because you're not it's like the coefficient depends on derivatives, but you count what is the main derivative. It's a little bit like you have a Burger's equation where your A of Ux, U depend on Ux. But it's still a first order PDE, right? It's not a second order PDE. Okay, anyway, so this is a surface diffusion and the Willmore flow, complicated, and you can actually get LDG methods and prove energy stability. That's in this paper. Okay, so this is a summary of LDG methods for diffusion equations, diffusive equations. So that includes fourth order, sixth order, and so on, and several typical examples. Now let me summarize LDG schemes for dispersive wave equations, which means the odd orders. So it's the first order, well, first order is hyperbolic conservation law, so third order, fifth order, seventh order, and so on. So this is, well, I already mentioned the third order, right? So that's the KdV type thing we have seen before. So the fifth order derivatives, you get this. So this is the first order derivative. This is the fifth order derivative. Yeah. 5 derivatives. Yeah. Okay, then you can get the cell entropy inequality and the L2 stability in this thing. Oh, I don't have pictures, sorry. I think when I was preparing these notes, I took out a lot of things because I thought that I couldn't cover too much in 3 hours. So this is the KMN equation with the M here and N here. So nonlinear in convection, nonlinear in dispersion. This ends up with the so-called compactone solutions. So some kind of things, isolated structures which moves. But it's not solitone, it's called compactone. It's completely compact, I think. For this, you can actually prove Ln plus 1 stable. So I want to emphasize that the stability for different systems could mean different things. Energy could be a different, it may not always be L2 stability. For example, here, if N is 3, this will be L4. So for KNN equation with odd N, you can obtain Ln plus 1 stable LDG scheme in this paper by Levy, Shu, and Yan in many years ago. So we have this scheme. And the KdV-Burgers equation. So you have the KdV, nonlinear KdV here, but also diffusion here. So there's a dispersion, there's diffusion, there's a convection. So this is complete with every mechanism. You can prove, you can get L2 stability for the scheme, L2 error estimates. The special case is KdV-Burgers. So you have the third derivative here with beta, second derivative here with alpha, and then you have the Burgers term. So for this, if you fix epsilon and fix beta, and change alpha, you can see that it's a fighting between the dispersion and the diffusion. The alpha, if the bigger the alpha, the more diffusion the problem becomes. So you can see that if here alpha is 0.5, you get basically a diffused shock front. If alpha is 0.05, you get some dispersion, right? Some oscillations. If alpha is 0.001, 0.0005, then you get more oscillations. So it's a fighting between diffusion and dispersion, this system. Fifth order KdV type equations, you have all these nonlinear guys. And this is a prototype. You can show that this one with this compact initial condition gives you this thing. So initial conditions like this, then you get just a lot of waves going out. After all, you have the dispersion effect in this equation. Okay, the fully nonlinear KNNN equations. So first, third, 5, all with N here. So it's a KNNN equation. You can get a kind of an LDG scheme, which is Ln plus 1 stable. So basically, the LDG scheme has a lot of freedom that if you have a PDE from mathematical physics or some applications where physicists derived them using a certain energy, most of the time they do have this built-in energy. So it's describing some physical phenomenon. So there is a positive quantity nonlinear function. Maybe the L2 norm, maybe something else. That is ddt of that is less than or equal to 0, or equal to 0, which means energy conserved. Less than equal to 0 means energy diffusive. So then your task is to see, first of all, how do they prove this fact for the PDE? There must be some mathematicians who have worked out the proof. You look at their procedure, their proof. Then you try to mimic that. You design your DG scheme by choosing your numerical fluxes suitably. You try to repeat the proof for your scheme. Of course, it depends heavily on the choice of numerical flux that you choose. Because comparing with them, with the physics proof, that has no interface terms. This is completely internal and physical boundary. But here you have a lot of internal boundaries which produce a lot of garbage terms from the interface. You would want to choose numerical fluxes so that these internal terms that you pick up are either canceling with each other or they produce a term with a correct sign, with a positive term on the left or a negative term on the right, so that then you get the stability out of it. I would not want to claim that it is always possible, but you can see from this very extensive list that it is indeed, it has been done for many, many very complicated nonlinear PDEs in mathematical physics. Okay, and this is Schrödinger, also very important wave equation, but this one doesn't belong exactly to even odd derivative because of this I. Even if this is a second derivative, it is still a wave equation, so it's a special case. Usually I use this as an exercise in my first graduate course in finite difference. I asked them to perform a stability analysis, design a scheme, perform stability analysis. A lot of people get confused because they remember for second derivative I should use what, and first derivative I should use what, but this one you should use techniques from first derivative because it is a wave equation, right? So it's because of this I. But anyway, you can design LDG schemes which are stable, satisfy cell entropy inequality, L2 stable, and with L2 error estimates, sorry. The good news here is that for the nonlinear Schrödinger equation of this kind of nonlinearity, you can actually have blow-ups of the solution at a finite time. So this is known. For example, you can actually, from this very nice initial condition, you can get this solution, right? In finite time, in 0.108, you get actually a blow up of the solution at a single point. So this kind of behavior, again, calls for numerical schemes to be adaptive. So hopefully you can put a lot of things here, and then maybe high order polynomial degree, or both. Actually refinement, high order degree at this location so that you can save computation time. This is not done though in this test. We use a uniform 120 by 120 mesh, but it should be done. So that's one way to say this DG has this flexibility. Okay, Ito type coupled KdV equations. So this is a coupled third order system. Ito's equation here, and you can get also. These should be Russians, right?
Yeah.
Yeah. So KP equations. So I.
Plasma physics.
Yeah. Kodomosiv. So I call them KP equation, right? So cannot pronounce the name correctly. Anyway, so and they also have KP1 and KP2, meaning the sigma square. Even though it's written as a sigma square, it could be a negative number. So if it is -1, it is one type. It is +1, it is another type. The equation, this one actually took us a lot of time. This was actually Yang Xu's PhD thesis, so it was given to her at the beginning, but it took her a lot of time to finish because of this extra x derivative outside. So you can see that you have this UT with an extra x derivative. That means your solution is not unique. Your solution is unique only in this restricted space. Because otherwise you can add a constant, it will still be a solution, right? So, but if you add a constant, of course, this is no longer less than infinity. So in this class, the solution is unique. So then it takes us some time to figure out a correct formulation of DG scheme, which actually later worked out very nicely. So you can prove L2 stability in this class. And you get the solutions which look like that. So T equals 1.5. I think this is KP2. So KP2, you get this kind of structure, very beautiful structures. Okay, so ZK equations, we just use the first letter. Again, Russian, right? Yeah. So ZK equations, there's L2 stability, commas are home. Hunter-Sexton equations, this is a fifth order derivative, and the generalized Zakharov system. Yeah, anyway, turbulence in the plasma. Okay, yeah, you can actually get two conservation or energy conservations for the LDG method. DP equation. Yeah, too many such equations. So basically, what I would like to say is that before the break, the LDG method is sort of, I would say, as a machinery that has a lot of free flexibility by tuning the numerical fluxes to obtain good schemes for many nonlinear equations coming from mathematical physics or applications. So you should first, once you face a new equation, what you do is that first you distribute it to one of the two bigger classes. It's a diffusive equation for leading term is even order derivative. Our dispersive equation where the leading derivative is odd order. Then the even order, the guiding principle is that you introduce alternative variables and you do pairwise alternating choice of fluxes. And these odd ones, you introduce the auxiliary variables, you do pairwise alternating, you leave the middle guy to be upwinding. So these are big guiding principles. Then, of course, to special cases, you have to look at how the PDE, what is the energy for that PDE, how do they prove energy stability for that PDE from a PDE point of view, and then follow that proof, get all these interface terms and see if you are lucky that these interface terms would disappear. They cancel each other, or they produce a term which is positive at the correct side. So then finally you can go to the computer and safely. I would say that it's important to do this first before going to the computer, because at the beginning, for some of the complicated PDEs, we were unable to get this energy stability. We just went to the computer by some educated guess of the fluxes, but sometimes it just doesn't work. So it pays to spend the time to sit down, work out the correct way of doing the flux. And then you can be assured that it should work. So if it doesn't work, then you can be confidently telling your student that, no, that's your coding error. But otherwise, right, if the student says it's unstable, you take his or her word. It could still be coding error, but you could say, well, that's maybe the scheme. So it's important to work out the theory this way. So future work is basically I was saying that design stable DG schema nonlinear dispersive diffusive equations. This one you mentioned also, time discretization. There are recently many papers on this now. So how do you treat time in an efficient fashion? I think the best way would be preconditioned iterative methods for implicit solvers. Because implicit solvers, first of all, would give you some very good, sometimes unconditionally stable, but at least many times much larger time step allowance. But of course, you have a nonlinear system. So how do you solve that nonlinear system? You basically shifted the difficulty from one to the other. And in the nonlinear system, the best way would not be directly using Newton or so on, but then you would lose the advantage of DG. You should still use sort of a pseudo time marching, which is called iterative. So each iteration is still more or less a time marching, so that you can use this local data structure and everything very nicely. But you want to put some preconditioning, which means pre-multiplied by some matrix. So that would then plus iteration, sometimes multigrade and other things. Let me try to summarize. Basically for the even orders, 4, 2, 4, 6, and so on, people have figured out very good multigrade methods for DG. So it's essentially the same efficiency as the usual finite elements. So even orders are fine. Odd orders are tougher. So the third order, the fifth order, the seventh order, first of all, multigrade usually doesn't work very well for this kind of non-symmetric, non-positive definite systems. They don't work very well. And preconditioning depends on the equation itself. So sometimes it works well, sometimes it doesn't. So this is for the odd order. There are still a lot of research going on here, people trying to figure out a good way because this I would say is the bottleneck. If you use explicit, you immediately find out it's impossible. The time step is, for example, third order PD, the time step delta t is delta x to the cubed, right? That's very, very small. So how can you tolerate such small time step? So you really have to find out a good way to solve this time discretization issue. And error estimates, and with the goal of doing adaptivity, I would say. So some a posteriori error estimates to guide adaptivity would be nice. Okay, so I think we should stop here for a few minutes and then move to some recent developments. Okay, so let us continue and to get to the last part. So the last part will be a few recent developments and applications of DG schemes for higher order PDEs. I have planned for 3 topics. Let's see how far we can go. The first one is positivity preserving finite volume and DG schemes, which we mentioned actually on Friday, but for hyperbolic equations. You can extend this technique from hyperbolic equation to parabolic equations in 2 directions. The first direction is the so-called non-standard finite volume scheme. In this paper, with Xiangxiong Zhang and Yuanyuan Liu and myself, we designed a so-called finite volume scheme, but it's not the standard finite volume scheme. This particular finite volume schemes framework allows us to directly generalize the positivity preserving technology from convection equation to diffusion equation. So let me explain this particular non-standard finite volume scheme. So let's again use heat equation 1 dimension as an example. The traditional finite elements would use just a single, so integration over the cell as divided by the cell length, which is called cell average as the computational variable. This non-standard thing uses the so-called double cell average, which means you do the cell averaging operator once, and you do it a second time. So you can think of the cell averaging operator as an operator, right? Basically at each location x, you just average around yourself with length x. You integrate in an interval which is length x around yourself divided by the cell length. So if at every point you do this, you get a new function, which is the cell average function. And you apply the same cell averaging operator to that new function one more time, then you get this so-called double cell average. Why is double cell average good? Because if you do double cell average on this equation on both sides, you do the double cell averaging operator on both sides. On the left, you get this DDT of the double cell average, or without this 1 over delta x squared. On the right, you just, if you integrate twice, it's a second derivative, you just get this traditional central 3-point scheme. It looks like a scheme. Notice that 48 is not a scheme. 48 is satisfied by the exact solution of the heat equation. Exactly. So this very much likes the finite volume scheme for conservation laws, right? Finite scheme for conservation, finite volume scheme for conservation laws is that you integrate the conservation law once. You get something similar to this with only 2 terms flux difference here, and then you convert it to a scheme. We do the same thing. So basically we start with the double cell averages, then we design a scheme which looks like this. That is, we evolve the double cell average. So at time level n, we have the double cell average. We perform a reconstruction. This time, the reconstruction is to reconstruct a function ux from its double cell average. So it's slightly different from the standard reconstruction, where you reconstruct a polynomial from a single cell average, right? Now you have the information of double cell average, but still, it's okay. So you have double cell average, you reconstruct a polynomial whose double cell average in each cell agrees with the given double cell average. It's the same procedure. So you get the polynomial, you can still do Wano, you can still do anything you like. You basically reconstruct these point values from the double cell average. Once you do that, you put them in here, you have a scheme. And for this scheme, then you evolve, for example, in time using Euler forward or TVD or SSP, time discretization for explicit. For implicit, you do something else. For this scheme, you can basically, I will not explain the details here, but you can basically take the maximum principle preserving or positivity preserving technique I explained on Friday directly over. Very little change. In other words, you have the reconstructed polynomial, you limit them at some quadrature points, and that's enough. So you just right? You read them at several quadrature points, compute the theta, scale the polynomial by this theta, and then put it back to the scheme, and then the scheme will be both uniformly high order accurate and positivity preserving. So exactly identical to the results obtained for hyperbolic conservation laws, you now get a scheme for both heat equation and the nonlinear convection diffusion equation that you use this double cell average based non-standard finite volume scheme, you get high order accuracy and positivity preserving or maximum principle preserving. So this is one possible way. So this is in this paper here. The only drawback of this approach is that this is not your standard finite volume scheme. So I don't know how many people will be willing to throw away your finite volume code and do this, because it's a double cell average. After all, you have to recode, right? Because the reconstruction subroutine would be different. The constants would be different. A lot of things would be different. The spirit is the same. The structure of the code is the same, but a lot of details will be different. But I would say this is actually a natural way to do, and it should be the correct way to do, because for high order, you see the second order, you have the second order derivative, you should use double cell average, right? One derivative you integrate once, two derivatives you should integrate twice. So this should be a natural way to design final. But of course, I'm not arguing with people, and I don't expect people to pick this up very quickly, because it involves recoding, and if anything that you need to recode, you have resistance. So unless your current code doesn't work, then you probably would be willing to spend the time to do this. If it works, it's just a little bit, yeah, who cares, right? Then you would not do this. So this is one possible way. The other way, what do you do if you don't want to do this? You still stay with the usual finite volume or the usual DG. Then, unfortunately, all I can say is that we only know how to get this maximum principle preserving or positivity preserving for piecewise linear case. That means our result is restricted to second order schemes. So this is in sharp contrast with the hyperbolic case I discussed on Friday, for which we can go to any order of accuracy on any meshes. Here we also can go to any meshes. However, we have to restrict ourselves to second order accuracy. So that's, and it took us a long time trying to overcome this barrier, and we were not able until now. And there are some essential difficulties, so maybe in our approach, this is a barrier very difficult to jump over. Maybe we need a different approach. So on the other hand, the P1 case, the second order case, the procedure is very simple. The procedure is the following. It's the same as in the hyperbolic case. So if P1 is simple, even quadrature points you can forget. P1 on triangles, on any shaped things, you only need to read at the vertices. So three vertices, you have three values. If you control these three vertices, then the whole function will be in between, right? Linear function. So basically the theta, the scaling factor theta, is computed from evaluating your old polynomial at the three vertices of the triangle. Compute the theta, scale the polynomial, throw it back to the scheme, that's it. So no matter what is the shape of the triangle, used to be that in many earlier finite element proofs, they need the triangulation to be acute or to have some restrictions on the angle. It is not here, so this restriction is not here. So we can prove rigorously that you do what I described before, then under certain CFL conditions, your scheme will be, A is uniformly second order accurate, and B, it will be positivity preserving or maximum principle preserving. So this will be a very nice thing to get, but unfortunately, we know how to do it only for second order accuracy. The difficulty, I don't know if I know. Yeah, I did not mention the difficulty here. The difficulty to trying to generalize this to high order is that exactly before I sort of hinted, the PDE is a second order PDE. So if you want to get back to point values, you have to integrate twice. So if you integrate only once in this DG formulation, basically the cell average is similar to the regular finite volume scheme. But the double cell average is not similar to the double cell average scheme that I introduced. So if you only look at the single cell average, you don't get back exactly to point values. You get back to some intermediate stuff, which corresponds to first derivatives. But on the other hand, you should not limit the first derivatives. You should limit only the point values, right? This is, you agree that you should limit the point values, right? So the derivatives are much more difficult to control. So if you limit only point values, but you integrate only once, there is a gap between what you do and what you wish. So roughly speaking, this is the story. But of course, there are technical things that you get some technical contradictions. This is the wish list. This is what you can do. They don't overlap. Anyway, so this is less satisfactory. There are attempts to get a higher order DG method by other DGs, for example, direct DGs. So this Jue Yan, my former student, is trying to do some work in this direction. So the second order result is here, but that's only second order. So this is the first recent development I would like to mention. The second recent development I would like to mention is a multi-scale DG method. This one, the multi-scale itself probably is not all of you would be interested in, but I want to emphasize some underlying sort of general principle here. So to demonstrate under what situations you could expect DG schemes to be of advantage. So here is the setup. This is actually a linear problem, second order elliptic equation with a coefficient which doesn't depend on u. It depends only on the location x, but it is an oscillatory function. For example, it could be oscillation it could be depending on both x in large scale and x over epsilon. Epsilon could be a very small number, so it means it could be a very oscillatory coefficient. But it doesn't have to be this way. It just can be, it can have continuous oscillation scales from epsilon to order 1. So it's a lot of scales in this. The objective, of course, is to solve this PDE 50, not in a mesh which refines epsilon. For example, if epsilon is 100, then the coefficient has 100 waves from 0 to 1, 0 to 2 pi. 100 waves. If you want to put at least 5 cells per wave, then the minimum number of cells you need to use would be 500. And in 3D, this is already a cost you cannot take. So the idea is that you don't want to do that. You want to use a very coarse mesh, maybe 50 by 50 by 50. Then, of course, each mesh contains several of these oscillation periods. Then forget about using polynomials as your approximation, right? If you use a polynomial linear function to approximate such a thing, it cannot be accurate. So you would have to use different basis functions, which are by themselves oscillatory. Now, here, DG method has a huge advantage because, like I mentioned before, DG is flexible for P adaptivity. Again, in this situation, the DG is good because I am in this cell, you can give me any basis you want. I will use you in this space, for example, some oscillatory basis functions here. My neighbor could use regular polynomial, or could use another different set of oscillatory functions. You could use anything. So what I use in my cell has nothing to do with what my neighbor should use as basis functions, because we don't enforce continuity along this line. So technically, the DG method is very friendly to multi-scale methods which use non-standard basis functions and use basis functions which change locally. So you use a set of basis functions, your neighbor use another set of basis functions. Impossible to enforce continuity, hence impossible to be implemented for continuous finite elements. Like on a continuous finite element, you have to enforce continuity here. And this is one of such cases. So you can see that we just use this DG approximation space, which is, you see the thing is that this is a phi. It's probably not very clear. This is a phi. You see the good news here is that this f here does not have epsilon. So this is very typical. F could even be 0 in many applications. The coefficients are usually, for example, in porous media, what is this A epsilon x? It is the structure of the soil, for example, so your water is flowing in this medium. So the structure of the soil underneath or rock or whatever, they have very different A epsilon x. They could be very different over the place. But the right-hand side is 0, or is some given function f, which is very smooth.
Like gravity, for example.
Yeah, gravity also. So the f can be approximated by polynomials very well. So in this case, this is your space. You choose a basis function who is oscillatory, but you apply the left-hand side operator on it. Let's say if you get 0. So that is, I use just right-hand side, I just approximate the leading term. You get 0. Or you get not 0, but a polynomial of degree k minus 2. So the idea is that in these kind of basis functions, I can expand the right-hand side by polynomials, right? Because you put these fancy things, you put the operator on it, you get regular polynomials, hence you can approximate the right-hand side very well. But of course, these phi themselves look very funny. So that's another difficulty. These phi themselves will look very oscillatory, and if it is impossible to compute those phi, and you cannot write down formulas for this phi, or you have no easy way to compute this phi, then the method is not very useful. For example, there are attempts to compute those phi's again by finite volume, by finite elements, using very refined mesh to compute them. But if you do that, then the cost of computing phi is sort of equivalent to compute the original problem, because it's, right? You have to solve this. This is the same equation as before. The only thing is that, of course, the cell is smaller, but not much smaller, because at the end of the day, you want to use 50 by 50 by 50. So it's only 150 smaller than the whole domain. So you are not saving too much if you have to compute this phi numerically. So I would say these kind of methods are useful, first of all, of course, in 1D. Later I'll show you how to write down the solution, write down this phi. Also in multi-D, but in a very restrictive, but I'm told very useful application. In other words, these coefficients are oscillatory at any physical location only in one direction. So the major oscillation is in one direction. In the orthogonal direction, the coefficient A is much more regular. You ask, is there such an application? Yes. In semiconductor devices, for example, there is an outside force called the electrical field. The oscillation is mainly along the electric field. Orthogonal to the electric field, the thing will be very smooth. You can use polynomials to approximate them. So you can use tensor product basis of polynomials, one-dimensional oscillatory. This one-dimensional oscillatory thing can be computed by hand. I will show you later. So for this kind of applications, DG is really powerful because it's very fast. Because you write down the basis by hand, you don't have to compute them by computer, and then you just use them, and then you ask, why cannot you do this by continuous finite elements? Well, even though it's oscillating only in one direction, this direction does change over space. For example, the electric field is not a constant, so it changes gradually. It does not change on the epsilon level. It changes gradually over space. So you and your neighbor, even though the oscillating directions are very similar, there are still some deviations, delta x deviations. So you cannot use the same basis on these two cells. You use two different bases, hence there's no way you can enforce continuity along the boundary. But for DG, this is not an issue, because it's right. You don't need continuity. So perfect application for DG for multi-scale. So let's see the 1D case. Let me explain the idea in 1D first. So the 1D case, you have the A epsilon, the coefficient, which is elliptic, so the coefficient is bounded below and above by positive numbers, but very oscillatory. And these are the basis functions. You see, it's an integral of the coefficients times a polynomial. So these are the members of basis functions. I said you can compute it by hand because for many, if the A epsilon x is given, maybe you can open into mathematical tables and maybe this integral can be computed analytically. Even if this cannot be computed analytically, this is a one-dimensional integral. So you can use a quadrature, for example, one-dimensional quadrature to compute those bases once and for all, so it's not a big deal. If you want multi-dimensional finite element solvers, it's a lot of cost. One-dimensional integrals, you can use very refined quadrature points to compute these basis functions very accurately. So this is, so these are the basis functions. So you see, it's a DG method, but instead of using polynomials, I use these guys. So I write my solution UH as a linear combination of these guys, and I solve for the coefficients. So it's completely the same as before. It's a DG formulation, but instead of those 5 Ks being polynomials, now the 5 Ks are these guys. That's all the difference. Okay, then you can prove this kind of typical error estimates. If you look at it very carefully, it looks like a regular error estimate, but it is not. It says U minus UH in L2 is bounded by, K plus 1, that's fine, it's the same. However, this is not, usually this would be some Sobolev norm of the solution U itself. Then you are in trouble, because if you put U there, U is oscillatory, so the Sobolev norm is huge. Then it's useless. It's useful only when H is so small that you put several cells per wave. However, here, this is F. This is the right-hand side guy. That means you can use very coarse mesh and still get good error estimates. Right, so this is the multi-scale. So what you want to design a method that you can prove such a thing. By the way, this is impossible if UH is based on polynomials. I explained, right? So it's this guy. How can you use a polynomial to approximate it? But it is possible if you use these fancy guys. Okay, so then 2D. So 2D basically, this is of course this is earlier work that we know that the direction of oscillations, the coefficient here is only oscillating in X, only oscillating in Y. Then we can write down the basis and same error estimate. But here we can prove it for the 2D. We can prove it only for P1. You see here this is H square. So this works for P1. So it's not P1, sorry, I always use P1. It's called S1, which means it's similar to P1, uses 2 guys in the basis, but it's not 1 and X, but it's 1 and somebody else. That is that oscillatory guy. Okay, so that you can prove for multi-D as well. Generalized equation with curvilinear, this is what I said, that is at each point the coefficient is rough, it's oscillatory only in one direction, it's much smoother in the other directions. This oscillatory direction changes smoothly over space, exactly as I explained before. You are here, electric field is in this direction, you are here, electric field in a slightly different direction. So then, but at each location, there is an electric field pointing to an oscillatory direction and the orthogonal direction, which is non-oscillatory, much less oscillatory. And you can get exactly the same error estimate as before. Let me show you some computational results. So this is 1D. This is the coefficient. You can see that it has this kind of coefficients, which means it's oscillatory with continuous. So it's epsilon sine x over epsilon, but since sine x runs from -1 to 1 continuously, you have oscillations from 1 over epsilon to 1 continuously. So all scales are present. There's no scale separation in this example. This kind of numerical method has a big advantage. It does not have to require scale separation in order for the methods to work. There is another class of multi-scale methods which requires that you have a large scale You have a small scale, but you have nothing in between. There's a gap in between. If your situation is like that, then there are other methods, multi-scale methods, which can work. But if you have a continuous scale, spectrum, like turbulence, then you would have to use a method similar to this that is workable for all, but it does not require a gap in the scale, in the large scale and the small scales. So for example, this one. And then you can get, for example, U minus UH is second order. You can see that when epsilon is very small, you still have second order, right? So it's, if it's a regular polynomial-based thing, then with this small epsilon, with this coarse mesh, you're not going to get anything. Similarly here, second order. So this is 1D, you can still get third order for S2, which corresponds to P2, so sort of using 3 guys per cell. So 2D with the same non-separable coefficients. Again, there's no scale separation because this is sine x over epsilon sin. And this one, we have some, okay, so here is S1. Here is S2. I think for this one we have, okay. I think this one, if I'm not mistaken, for this one I don't have the exact solution, so I have to compute the exact solution, which restricts to how much I can go in terms of accuracy, because it depends on the exact solution's resolution. Remember, the exact solution is very difficult to compute. It's a very oscillatory guy. You need to use even spectral method. You need to use many, many points to compute it accurately. Okay, so these are the papers which are involved. Mainly the curvilinear case that is in each direction, I can change the oscillation, is in this paper, which is part of the PhD thesis of a student who just finished, Yifan Zhang, and which we have just submitted this paper. Okay, so finally, the last application, the last new development, I want to mention the so-called energy conserving LDG method for second order wave equations. Up to now, I have only considered first order PDEs, first order in time PDEs. In other words, I have only considered PDEs which are U sub t plus something else equal to 0. This something else could be first derivative, second derivative, third derivative, and so on. But U sub t is U sub t. Now I would want to talk about the PDEs which have U sub tt here. Of course, you say, well, this is no big deal. U sub tt, people know already for a long time that you can introduce, again, auxiliary variables to rewrite this second order derivative into a first order system. So then it is a standard first order hyperbolic system. You can use a standard DG method to solve it. This is the point of view that I myself adopted for a long time. So I have not bothered to look at the DG scheme for this equation at all for a long time. Until my student Yu Longxin graduated, went to Tennessee, University of Tennessee and the Oak Ridge National Lab, worked with people there. He worked also with big shots in KDV equations like Jerry Bona. And then since he left me, he's less influenced by me. So he was telling me, this second derivative thing, and there is also something new there. So it's not that you can always convert it to first derivative and solve and get everything done. At the beginning, I was asking what is new. He said, well, these people ask us for energy conservation, exact energy conservation for your scheme. And I scratched my head. I was saying exact energy conservation. Look, this is a hyperbolic equation. So if it is exactly energy conservative, then because I have this idea of entropy solutions and so on, right? So I was always thinking that hyperbolic conservation laws cannot be exactly energy conserved, which is true, because the entropy solution, the entropy the exact entropy solution dissipates energy. The L2 norm is not conserved for nonlinear hyperbolic conservation laws if your exact solution has shocks. Shocks dissipates energy. So I always had this feeling, that idea. I said, no. You need upwinding, you need numerical dissipation because you have this entropy condition. You have that. However, it's two different worlds, right? For them, there is no shock. For example, in this equation, or maybe there's a coefficient in front, but the coefficient is a smooth coefficient linear. There is actually no shock. So if there is no shock, then the physical solution does conserve energy. Then you can argue that if your scheme conserves energy, whether it will be of any advantage or not. Even that, I was at the beginning, I was questionable about this, so I told Yulong, I said, look, you can compare the two schemes. One is dissipative, the other is energy conserved. You can compare the results on the same mesh, you see which one is better. He looked at it for regular t, for example, t equals after 1 or 2 periods in time, and you refine the mesh. Certainly the upwind one is better. I know that. So the upwind one is performing much better than the energy conserved one in terms of numbers of errors. So you look at 10 to the minus 4, 10 to the minus 5 on the mesh. These numbers are better on the upwind side than on the energy. So I said, look, see? However, to my dismay, if you run this for very long time, like maybe 100 periods, 200 periods later, things change. Actually, the dissipative one becomes less accurate than the energy conserved one. So this I did not know. So this, you could call this structure preserving or something like that, that you keep some physical things invariant, for example, energy, could help you for long-time simulations. So, okay, so then I agreed, okay, fine. So you need, in some situations, energy conserved DG schemes. But then how do you do that? Okay, so again, I said that for this PDE, you can rewrite it into a hyperbolic system. Once you write it in a hyperbolic system, it's a standard hyperbolic system. It's UT equals to capital A times UX, a 2x2 system. For that, you can use upwind flux. You get an upwind scheme, which is energy dissipative. You can also get an energy conserved scheme by choosing the central flux. Left plus right divided by 2 as the flux. However, that is not a good choice. If you do that, your accuracy is degenerated. So you no longer get the optimal h to the k plus 1 order accuracy. So you cannot get both. On energy conservation, then you lose accuracy, at least for that system case. And people actually spend a lot of time trying to overcome that difficulty. For example, Enquist has a paper which they introduce some very funny looking DG operator with DG space which break in the middle of the cell. So in a cell, it's not a single polynomial, but 2 polynomials linked together. So it's very complicated in order to overcome this difficulty. So we don't want to do that. We want to use regular DG, regular fluxes, just change the flux, get conservation. And to my surprise, you can actually do it without writing to first order system. Just keep it second order. So sometimes the second order PDEs are of some advantage. So this is a surprise to me, I have to admit. So if you have this second order PDE, yeah, this is what I murmured. I already murmured, and now I wrote it here, that for nonlinear hyperbolic, upwinding is important, but for linear with no shocks, energy conservation might be okay, might be important. Then energy conserving, yeah, is suboptimal if you do it in the system case, but you can do it. Yeah, I mentioned Enquist here. I'm probably jumping without flipping the transparencies. I mentioned Enquist here, that in order to obtain an energy conserved DG method for the system case, you would need to do special things. However, it turns out that you can get an energy conserved DG scheme for the second derivative original equation very easily. So here is the result. So you keep the TT, so first of all, let me keep the T variable, and later I will mention how you discretize the T variable. You keep the TT semi-discrete. You still do LDG. In other words, you treat the X derivatives by LDG, T derivative, you leave it alone. And you just use good old alternating flux. Of course, you say, doesn't make sense. Isn't alternating flux for diffusive equations? Yes, but this again is a second order PDE. So your good old experience doesn't work anymore, right? Here it's UTT. So it's the games are sort of different. So here you can actually use this alternating flux on the spatial operator for UXX just as if you did for the Healy equation formally. And would you believe just that gives you an energy conserved scheme which is optimal order convergent. I did not expect that, at least I myself, I did not. I mean, the literature, you can see that there are a lot of internal penalty type methods which cannot actually get energy conservation because of this alpha business, right? You put an alpha there, it's very hard to get true energy conservation. They get some kind of conservation with a modified energy which has this alpha in it, but then physicists don't like it. So that's not energy, that's something else. So here, you don't have parameters, you have a very simple choice of numerical fluxes, but then the method is already energy conserved. So you already have, where did it go? Yeah, oh, I'm sorry. So I probably got lazy. It's late evening when I prepared this, so I just put one sentence here. I did not put the formula. But we obtain both energy conservation and optimal L2. So basically what you get is that ddt of UH squared integrated is 0. So the energy doesn't change with time for your numerical solution. Is it UH squared plus? Yeah, so it's the true total physical energy. It's probably UH squared plus UT squared, UX squared plus UT squared. That's the total energy. Okay, so this can be generalized to with second order wave equations in heterogeneous media. That is, the coefficient doesn't have to be constant. It can be depending on X, it can be discontinuous. Coefficient can be discontinuous. The solution, it has no shocks. Then you can have variable coefficient. You can have multi-dimensions. So these are the two papers. This is basically 1D setting out the method given the proof, and this is the multi-D with also variable coefficients and so on. Yeah, so this kind of methods, let's see if I have a picture here. Yeah, there's a picture here with some solution, exact solution. There are some words here, you don't have to read it, but you just have to notice that T is very large. T is very large, so it's a long time behavior. And then you can see the comparison of our method, which is this guy, with some internal penalty DG. So this is the error accumulation in time. So this is the same mesh. And this is the time variable, and we are plotting the L2 error with time. You can see that in this n equals 40 case P2, n equals 40 case P3, the errors are basically, well, at least in this scale, basically constant in time for our method. So the energy conserved method has a better way of maintaining the long-term accuracy, or in long term, So basically fluctuates, but basically pretty flat in time. While the internal energy thing, it actually, the error increases pretty much. Initially at least increases very fast, and later it's still in this scale already, you can see with your eyes with increase in the error. This is for the same kind of mesh. Yeah, this is 80. Same pattern, basically, same pattern. So that means, yeah, it's a surprise to me also that sometimes if your target is to compute certain wave problems for which your waves are smooth, never any physical shocks, but it can have complicated structures, and you want to simulate it for a very, very long time, then maybe you want to design an energy conserved method rather than an energy dissipative method using upwind, even if it is a wave equation. So actually, Yu Longxin also designed energy conserved method for KdV equations. The method I introduced previously in the previous hour for KdV was dissipative because I used upwinding, right? For the middle guy, remember, I used the upwinding flux. So the method was actually dissipative. You have numerical dissipation. Even though it's high order dissipation, it's still dissipation. But you could design also purely conserved numerical methods for KdV, and also he showed that for a very long time you actually gain. For short time you don't gain, you actually lose. But for a long time you actually gain in terms of accuracy. Okay, great. Let's see. Yeah, here you also see cuts. You can see there are three things here in this picture. This is for a very long time. T equals 1,000, 40 cells. You can see only two, right? But there are actually three. There's IPDG, there's LDG, there's the exact. The LDG overlaps with the exact in this curve, so you don't see it very much. But the IPDG has a phase shift. So in other words, the exact maintenance of physical energy seems to be important. This IPDG actually also maintains energy conservation, but for Fanning energy. So it is artificially defined energy that the DDT of that is constant. But that seems not to be enough. You really need to maintain the physical energy in order to get long time sort of accurate results. Okay. How about that? Yes.
In the last scheme, current number is hyperbolic or parabolic?
For the last one,
yes.
It is hyperbolic. It's delta t over delta x.
Other questions?
You mentioned double cell averaging. Do you try average 3 times?
Yes, that would be for KdV. Right. But I would expect nobody other than myself to code it, right? Or maybe a student say, if you don't code it, you don't get your degree. So then he codes it, then he runs away to Wall Street.
It's really hard working, so. Any other questions? I have one question. The energy which you mentioned is not the same energy as in gas dynamics, apparently.
I guess it is equivalent to the L2 energy of the symmetric system.
If, say, I put initial condition as a shock wave, then I model with a conservative scheme, I would imagine that the total energy will be conserved.
Yeah,
So
first of all, this is linear, so you should compare with linearized Euler, like acoustics.
Because you mentioned that shocks, entropy production.
Oh yeah. If there is real shock, forget about these kind of methods. I don't think they will work because it's non-physical, right? You cannot really treat shocks with an energy conserved scheme. So that's why I had a lot of hesitation of using them. But apparently, if there is no shock, there are certain situations which these kind of schemes have advantage.
But I was asking, in principle, even if you have one-dimensional shock, the total energy is still conserved. Because you solve with a conservative scheme, So you have time derivative of total energy equal to fluxes.
No. It's not that energy. It's not that energy.
It's not energy from the dynamics.
Right. It's not that energy.
So pressure plus rho u squared.
No. The energy is probably it's similar to entropy.
Okay.
It's similar to entropy. It's a positive quantity that is related. So, for example, for a symmetric hyperbolic system, it is the L2 norm of the exact solution. For example, if you have 3 components, you just square them and integrate. DDT of that integral of all the conserved variables.
Integral of energy squared.
Yeah, plus density squared plus momentum squared. But it is not, because hyperbolic, this gas dynamics equation is not symmetric. It is only symmetrizable. So you have to first translate it to symmetric. And then there are 3 new variables, not density, momentum, energy, 3 new guys. And them squared integrated. DDT of these guys will be constant if you don't have shock.
When you were talking about these highly oscillatory problems with highly oscillatory coefficients, so you used some special form of basis functions which were built upon kind of distance connected to the matrix of the coefficients, right? So usual Euclidean metric is changed to the metric connected with the matrix Aij. And can you use the same principle, say, if you deal not with an equation with highly oscillatory coefficients, which are given, but instead if you deal with nonlinear equations, say with where this coefficient matrix depends on the solution itself, and if you have highly oscillatory initial data, so to build this or maybe reveal these basis functions depending on the structure of solution itself.
Yes. Yeah, actually we have a paper from a PhD student, Lin Yuan, who unfortunately also went to Wall Street. But he had a very good thesis, a JCP paper, in which we explored exactly what you said. So we are on the fly trying to determine the basis. For example, we compute a diffusion equation with a boundary layer or internal layer. So we try to put in there some exponential basis functions with the correct alpha. In that thing, we based on previous time step solution determine this alpha and continue running, and we get some good results. Yeah. So yes. So the DG framework provides you with this freedom. You can use any basis, but how do you use them? You still need to play, sort of. Yeah. So we played with that in a JCP paper a few years ago.
But in principle, it can do the same with finite volumes.
You can do it with finite volume. Yes. Yeah. But then you have to you have to modify the reconstruction. Here, the advantage is that there is no reconstruction.
I only have to modify the matrix. Okay, I can store 2 matrices.
Yes. That's right. And there are people doing that, right? There are people who do exponential type basis in finite volume, trying to get a Mason principle and so on. Yeah. Boundary layer, yeah. Yeah, so we have this very nice, so a couple of cells resolves boundary layer very well with this basis. Yeah. So, but yeah, you should try. Yeah, so Lin Yuan, actually, I was asking him to try Navier-Stokes and so on, but then of course he went to Wall Street, so forget about that. Wall Street doesn't have boundary layers, so they either oscillatory or drops immediately. Yeah, I didn't mention, I'm sorry. Yeah, so the second order is just the usual leapfrog type thing. But then they have a sequence of, I did not notice that they have that. They have a sequence of even order in time, energy conserved, explicit time discretization based on leapfrog. So you just use a few more layers and you can get the, yeah. So this is in the paper, yeah.
Could you say, if I'm right, if we speak about skin viscosity, the last skin, does it provide less or zero skin viscosity?
Zero viscosity. So that's why it's surprising that it works. Yeah. It will not work. Actually, there was a referee for that first paper and say, what happens if there is a shock? Then we computed with a shock. It's horrible, right? The result looks horrible. Then we basically replied with the truth and say, well, this is not designed for shocks. So you have to switch to another scheme.
I think any central scheme.
Because this second order equation could also have shocks. If the coefficient depends on u, it becomes a nonlinear wave equation, then you could have shocks.
Because if you reduce it to a system of two first order equations,
Yeah, each of them, if it's non-linear, each of them could have shocks. Yeah. If it's linear, then you have shocks only if you put it in. If initially it is smooth, it stays smooth. Or boundary or initial, yeah.
like for Boltzmann equation from boundary.
It's only initial or boundary. Yeah, it cannot generate these things. Yeah. But for nonlinear, they are generated, so you basically have no hope to use this kind of schemes.
Any questions? We don't answer questions. So let us thank the speaker again.
Thank you.